All right, welcome back, everyone. So our final speaker is Shrawan Kumar from North Carolina Chapel Hill. I don't see a title on my thing, so I'll let you announce your title.
Yes, I will have the title.
Okay, and I guess I was just told to announce if anyone wants to exercise their brains instead of their bodies instead of their brains this afternoon, you can get a pass at the Ramsey Center, the gym on campus for $10. All right.
Thank you. I'm very pleased to speak in this conference honoring my friend Dan on this special occasion of his 60th birthday. I don't remember exactly when I first met Dan. Maybe he remembers, but at least it was in the last millennium. That much I remember. And it has been my privilege to have known him. From the first time we met, we connected very well. And not only we connected very well with him, but with his whole family, his wife, who is somewhere here, or maybe outside. She's there, she's there. And also their two beautiful daughters, whom I have talked sometimes. So I, of course, admire Dan's work, which many of us have seen in some of the talks here. But apart from that, also I admire his mentorship of a large number of postdocs, graduate students, and undergraduate students. So with this small note, I want to congratulate him on this very special birthday and wish him many years of very active mathematical life and otherwise. Okay, so with this, this is page 0 of my talk. Can you read it? It's little down. Okay. Is it okay now? Yes, yes. So the aim of this talk is to give a brief outline of theory of twisted conformal blocks, extending the classical Verlinde theory of conformal blocks to the twisted setting, which I will explain later on. This theory we developed systematically in collaboration with Jiuzu Hong, who is somewhere here, probably. Well, yeah. He's there. Okay, he's there. Yes. So even though we are not the first ones to develop the twisted theory, but we have developed the theory in great generality, not considered before. So the earlier work in this direction is due to Damiglione, Akira Damiglione, and some precursors of the theory are due to Ed Frankel, Zesny, and Kuroki Takube. But I had to first explain the theory in the non-twisted setting, the classical theory. So because of the time constraints, I will only give a very brief outline of the classical theory, maybe in the first half an hour. And then in the remaining 15-20 minutes, I will explain what does the twisted theory involve and how does it look. Okay, so here is the title. So this is the title is Conformal Blocks for Galois Covers of Algebraic Curves. So first, as I said, I'm going to outline the salient points of the classical theory. So we start with a simply connected, simple, complex algebraic group G, and sigma, which is a reduced projective curve. But I will assume that this curve could be singular, but it only has the nodal singularity. So for those of you who do not know what is a nodal singularity, it's the singularity such that Z times W equals 0. So it's crossing this. So that's the only singularity I allow in the curve. I don't require my curve to be irreducible, but I require it to be connected. Now by S, so S is some positive integer which will be fixed for this talk. some positive integer starting with 1. So by a S-pointed curve, we mean this curve sigma together with bunch of points, P1 through PS. But these points are distinct, and these points are smooth points. So I don't take any of these points to be the singular points. So
Scroll up.
oh, sorry. Yes. Thank you. Now we also fix the level, which is called the central charge in the theory. We have many talks have talked about central charge with maybe differing meanings. So we fix a central charge, which is a positive integer. And now I define this subset DC. Now H is the Cartan subalgebra, and I take the weights lambda in H star, which satisfy lambda of alpha I check is non-negative integer, alpha I check being the simple co-roots. And I take lambda of theta check to be at most C, where theta is the highest root and theta check is the corresponding co-root. And as I said, H is the Cartan subalgebra of Lie algebra of G. Okay. Now, affine Lie algebra. So affine Lie algebra G hat, probably I don't even need to define, but just for sake of it. So G hat is G tensor, say this Laurent series ring, direct sum a central element, capital C, a one-dimensional vector space generated by the central C. And the commutation relation is X tensor F, Y tensor G, is the bracket XY tensor FG, plus the killing form XY times the residue of DF times G, and I'm taking residue at T equals 0. Now this bracket is the normalized invariant form, which gives us theta equals 2. The norm theta square is 2. And X and Y are elements in the Lie algebra G, and F and G are the elements in the Laurent series ring. So that's the affine Lie algebra. Now, so the integrable highest weight G hat modules with central charge C, and central charge means the action of this central element capital C, which was in the definition of the affine Lie algebra. So this element capital C. So the action of capital C in this module is called the central charge of that representation. So this DC, the set DC, which I defined here. So those weights such that they are dominant integral weights together with the requirement that lambda of theta check is at most C. So this set DC exactly parameterizes the integrable highest weight modules of G hat with central charge C. And the correspondence, I'm just going to take lambda in DC, and the corresponding integrable highest weight module is H lambda. Now, probably many of you know exactly how this looks like. So H lambda will have the top piece, which is a G module, and the G module is given by exactly highest weight lambda. And the center is going to act by C. And then there is a unique representation which extends to a representation of G hat with the central charge C. Okay, so the basic object is the space of dual conformal blocks. And that is, so now it takes for its data, this S-pointed curve, which I mentioned. So it's a curve sigma and bunch of points, which are smooth points, exactly S many distinct points. Now I take this S-pointed curve and I take lambda 1 through lambda S. These are the weights, highest weights for the integrable highest weight module. These do not have to be distinct. And these lambda I are attached to Pi. So they are exactly S many, not necessarily distinct, ordered highest weights for these integrable highest weight modules. And you think of this lambda I to be attached to the point Pi. And now we define this H, this vector lambda, is you take the tensor product of these H lambda I, H lambda 1 tensor, H lambda 2, so on, H lambda S. Oh, sorry. Say it again. Thank you very much. Thank you very much. Thank you. Thank you. Right. Now, we take this Lie algebra, German G tensored with, we take the ring of regular functions on the curve sigma, but we remove the points P, all the points P1 through PS. So once we remove the points P1 through PS, we get an affine curve. I am stopping some of the technical things here. I mean, technically, I should say that every irreducible component of the curve at least has 1 point Pi, at least. Because I want the sigma minus P to be an affine curve. So since it's an affine curve, there are lots of regular functions on that. So the notation C of sigma minus P is the affine coordinate ring of this affine variety sigma minus P, and we tensor it with G. And it has the obvious Lie algebra structure, just the Lie algebra coming from the G part, and there is no central charge here. Sorry, there is no central extension there. Now on this H lambda, or H vector lambda, this Lie algebra acts. And I am going to say, right, how does it act? I will say it in a minute. But now I define the dual conformal block, which I denoted by V sigma P lambda, which is this H vector lambda divided by the action of this Lie algebra on H lambda. So you are taking the covariance of this Lie algebra action on H lambda. So those of you who prefer this, is the Lie algebra homology, H lower 0, of this Lie algebra with coefficient in H lambda. Now, as I said, the Lie algebra structure on G tensor C of sigma minus P is exactly, basically the point-wise Lie algebra action. It's coming from the Lie algebra G. Now, I have to tell you how does this Lie algebra acts on H vector lambda. So that is, right. So that is, okay. So we take X tensor F, and always this notation X tensor F means X is coming from this finite dimensional Lie algebra, F is coming from some function, okay? So X tensor F acts on V1 tensor, V2 tensor, Vs, as you take summation from 1 through S, and in the ith factor, you take X tensor F Ti. So this is the Laurent series expansion of the function F, which is defined on this curve minus all these points Pi. So you take the particular point Pi, and you take the Laurent series expansion of the function at Pi. So you need to choose some parameter Ti. So you just choose a local parameter Ti at the point Pi, and you just take the Laurent series expansion of that. So that's the notation X tensor FTI. Now this becomes an element in the affine Lie algebra with respect to the parameter Ti. Now just act it on the vector Vi. So Vi was a representation. So Vi is an element in H of lambda I. And now X tensor FTI becomes an element in the affine Lie algebra. So this representation acts on that. It will produce another vector in the same H of lambda I. And you sum it. Okay. Now the point is, okay. Right. So 2 points here. One point is that this indeed is an action of this Lie algebra without the center. So G tensor C of sigma minus P does not have a center. So this Lie algebra acts on this H vector lambda. And that's a consequence of the residue theorem in algebraic geometry. So it's, slightly, involved. So you need to use the residue theorem in algebraic geometry for curves to conclude that this is actually a Lie algebra action. Okay, so now once it's a Lie algebra action, then we have this fundamental object, dual conformal blocks. That's V sigma P lambda is H lambda divided by this Lie algebra acting on H lambda. Now, the lemma says that this space actually is a finite dimensional vector space. Now, keep in mind that H lambda is infinite dimensional, it's very infinite dimensional, but this covariant space, this space of dual conformal blocks, is a finite dimensional vector space over complex numbers. Moreover, this space does not depend upon the choice of the local parameters, up to some canonical isomorphism, but this canonical isomorphism is only canonical up to some scalar multiple. Okay. So once you have a finite dimensional vector space, the first thing you want to know what is its dimension, right? So that's the most important and most simple invariant attached to a finite dimensional vector space, its dimension. Now, keep in mind that this dimension depends upon the choice of sigma, the curve, the choice for the points pi, and the choice of the weights lambda I are the representations attached to that. So those are three things which are needed to define this vector space. So this dimension depends upon, a priori, depends upon those three choices. Okay. So the question is, what is the dimension of this space? Now, Eric Verlinde, who is a math physicist, he conjectured in 1988 a formula for that. Okay. And I am going to give you a very brief outline of the proof of this. Now, he conjectured, and it's a theorem now for some years, but I'm going to give you a very brief idea. The proof involves it has lots of pieces. And the full proof, I know, it runs into something like maybe altogether 200 pages. But I'm just going to give you a very brief overview of the main ideas of the proof. Okay. So, and I do encourage any question. So the theorem number one is called propagation of Vakuum. What it says that this space of conformal block, I fixed points pi, I fixed weights lambda I, and I fixed the curve. So you keep the same curve, you keep the same points, but you attach one other smooth point. Okay. So let's just call it the point Q0. So I'm just attaching one more point, and to that point, I am going to attach the weight 0. So the corresponding integrable highest weight module is H0, but mind that it's not the trivial representation. It has central charge positive number C. So this is what is called the basic representation. Okay. So it's attached to the weight 0, but it's not the trivial representation. It's a still infinite dimensional representation. And this theorem says that the original space of conformal block is the same as this one when I attach a point. But I attach only the weight 0 to this extra point. Now, this is a very useful theorem, as probably you will get some sense. Now, the second, I would term it even more important theorem, is what is called the factorization theorem. Now, what it does, that let's start with sigma and a node Q on that curve sigma. Okay. So I am taking a curve. Unfortunately, there is no blackboard here. So
you can write it.
I can write it. Actually, that's true. I can write it. Yes. Oh, that's a good point. I can write it. Yeah. So I take a curve. but I am taking a node here. Okay. Now, this is a genus G curve. It's a non-smooth curve, so but still genus makes perfectly good sense. It's just the dimension of H0 with coefficient in the canonical one forms. Okay, so I take this node and I blow it up or normalize this node. So now I'm going to get 2 points over this node, and I'm going to get a smooth curve. Let's assume that Q is the only node on this curve. So I'm going to get a smooth curve, but the genus has decreased by 1. So I started with a curve of genus G, and I decreased to a curve of genus G minus 1. And you will see why it is so important. But let me first say the factorization theorem. So the factorization theorem says that let's take the normalization sigma height, which is now a smooth curve, a smooth projective curve. I should have said that. All my curves are projective. Okay. So now, over this point Q, I got 2 points. It's a node. So when I normalize, I get 2 points. So just think of this, that, okay, I have this, and when I normalize, I get this. That's the kind of picture I get. So now I got 2 points over Q. Let's just call them Q prime and Q double prime. So this factorization theorem says that let's take the original space of conformal block, V sigma attached to P lambda. And now I'm going to compare that with the conformal block on this smooth curve. So V of sigma height, I take the original those points, those very smooth points, so they are not messed up. Okay. In the normalization, I'm not touching them. They remain the same points. In the normalization, P height, but the point Q has become 2 points in the normalization, Q prime and Q double prime. Now I keep the same lambda I attached to the original points Pi, but now I attach to the point Q prime mu star, that's the dual of mu, and to the point Q double prime I attach mu. And mu runs over all weights in DC, the dominant integral weight for the integrable highest weight module. And I sum it up. And the theorem says, factorization theorem says that these two spaces are isomorphic. Okay. Now, the important point is, and this is part of the punchline. I wanted to calculate something on a genus G curve. I wanted to calculate the dimension of V sigma P lambda on a genus G curve. And this theorem tells us that we can do that on a genus G minus 1 curve, but we are paying some price that we are attaching 2 more points, and we have to sum over all possible dominant weights for the highest weight of integrable module for the affine algebra. But in any case, we have reduced the problem from genus G to genus G. Okay. Now, next comes, we have to simplify this notion of conformal block. And you will see in a minute why it's so important. So simplify means, I will not say all the technical definition, but simplify means that we took a curve, a single curve. Now I'm going to take a family of curves parameterized by some smooth variety T. So what it means that sigma T to T, there is a proper and a flat morphism. And every fiber is a curve of the type I mentioned earlier. It's a projective curve with only nodal singularity, blah, blah, blah. And I want sections now of this family, sigma T to T, exactly as many sections, such that if I take a geometric point in capital T, the fiber P1 through PS gives me exactly S pointed curve over that fiber. So I am basically simplifying this notion of a S-pointed curve to become a family over a parameter space. And I require these sections to be mutually disjoint because I want distinct points. Okay. Now, so then once I have done that, we can define sheaf of conformal blocks, just as we did earlier. So we shiftify this integrable highest weight module. We shiftify this Lie algebra. Okay, let's see here. Right. Yes. So we are going to shiftify this Lie algebra. We are going to shiftify this representation. And then we can talk about that. So this becomes a sheaf over the parameter space T. So this becomes a sheaf of OT modules, OT being the sheaf of functions on T. Okay, I will not give all the technical details. Okay, so now this becomes a sheaf of a sheaf over T, this the parameter space T. So the next important theorem is that let's assume that T is smooth. So far, I actually did not really need to for T to be smooth. I could have talked about basically over any parameter space scheme. But let's just assume that T is smooth. And this my pi is a smooth morphism, which has the consequence that all the fibers are smooth curves. Then, once we have that, then this sheafified version of conformal blocks. So this is a sheaf over T now. This sheaf admits a projectively flat connection. So this sheaf over T admits a projectively flat connection. And that's why I needed T to be smooth, because if you have a vector bundle over a sheaf over a smooth variety, you can talk about connection. If it's not smooth, it's more difficult to talk about that. Okay.
Did we already know somehow that this is a finite dimensional fibers?
Say it again.
So just from the definition, do we know somehow that its conformal blocks are finite dimensional?
That was already the first theorem I stated.
Theorem. Yes,
that was the very first thing I stated. Actually, it was not even worth calling a theorem. Okay. It's this lemma. Yeah. Okay. So now, since this sheaf admits a projectively flat connection, automatically it becomes a locally free sheaf. Once the sheaf admits a projectively flat connection, actually any connection, then it becomes a vector bundle. So this is a vector bundle. Okay. So that means that the dimension of the sheaf does not depend upon any point in the parameter space, as long as the parameter space is connected. Because it's a vector bundle, so all the fibers will have the same dimension. Okay. So this has this very important consequence that this vector space I talked about, the conformal block space, does not depend upon the choice of the points. And let's just assume that sigma is a smooth curve right now, just for a minute. Sigma is a smooth curve and connected a smooth curve, connected in any case, I'm assuming. So this theorem has the consequence that this dimension does not depend upon the choice of the points and does not depend upon the choice of the curve as long as we keep the genus fixed. Because if I fix the genus, then the curves in that genus, it forms a connected family. That's the result of the Verlinde and Mumford. And also you can continuously vary the points pi. So one important consequence of this theorem is that this dimension does not depend upon the choice of the points, as long as you keep those points smooth and distinct, and it does not depend upon the choice of particular curve of that genus. So now this dimension only depends upon the genus and the choice of lambda I. It definitely depends upon the choice of lambda I.
It still depends on lambda.
Oh, no. Choice of lambda I already has a central charge fixed. Lambda 1 through lambda I, they all have the same central charge C. And my two things are fixed once and for all. That's the number of points S and the central charge C.
Then we just saying you drop all the singular points.
This is again?
You drop the singular points.
That's right. Okay. So I dropped the, no, I didn't, no. The PIs are always smooth.
Yeah.
Pi are always smooth. My curve is singular, possibly. Right now, I mean, just for convenience, for this theorem, I'm saying that let's take the curve to be smooth, or the family is smooth family. But there is a generalization of this result, which works for non-smooth family as well. But then what happens is that the connection is not a honest connection, it's a logarithmic connection. But I don't want to, I mean, get into such technical detail. I want to give you an overview of the whole scheme. Okay, so now let's call this dimension of V sigma P lambda. It does not depend upon the particular curve, and it does not depend upon the choice Pi. So it only depends upon the genus and the choice of lambda I. So now legitimately I can say mg lambda, vector lambda. Now the factorization theorem, let's bring in factorization theorem again. Now it says that mg of lambda is summation mg minus 1 lambda mu star mu, where mu is running over dc. So now this mg lambda, that's the aim. We want to calculate mg lambda, and the factorization theorem says that now we can calculate that in terms of a g minus 1 curve, but we have added 2 more points. So we have to sum it up. And we can keep going, and we will go to a genus 0 curve. So this mg lambda becomes m0 lambda mu1 star mu1, mu2 star mu2, mu g star mu g, where mu i's run over dc, this parameterization of the integrable highest weight module. So we started with 10 points, and we added 2g, I mean 10 means genus with 10, and then we added 2g more points. So, but at least we are now to genus 0. Okay. Now, so now we have a problem which we have to confront. That is, now we are working on a genus 0 curve, but many, many points. Now, genus 0 means P1. That's the only genus 0 curve. Now, let's apply the factorization theorem again to a genus 0 curve.
Can I ask you a quick question about that summation formula?
Yes, absolutely.
Is that sum on the right finite?
Yes.
Oh.
No. Because, oh, absolutely. Good question. DC is a finite set. See, because I am taking dominant integral weights such that mu of theta check is at most C. So that makes it a very finite set. Okay. Okay, so what about I say? So now the problem we have is on a curve of genus 0, which is P1. Now I am going to apply the factorization theorem, and let's draw this now. And I am going to. So genus 0 curve, and I'm going to introduce a single node. That's my genus 0 curve with one single node. So I take 2 P1s and I just attach them at one single point. Now I'm going to normalize it. And when I normalize, I get 2 disjoint copies of P1s. That's exactly what I'm going to get. And this point Q becomes Q prime here and Q double prime there. And the factorization theorem is still available to this situation. So what happens now? Let's get to the right. So we had the problem about M0, but maybe million points, right? I mean, okay, million. Now, if I apply the factorization theorem, so what I'm going to do, yes, what I'm going to do, I had 1 million points, but I'm going to take lambda 1, lambda 2 here, and I'm going to throw lambda 3, lambda 4, lambda 5, so on, lambda 1 million. Okay. And now these 2 points remain those 2 points, and these million points, million minus 2 points, go here, but I have added 1 point here. So now I got 3 points here and million minus 1 point there. Okay. If I apply the factorization theorem, this side becomes M0 lambda 1 lambda 2 mu, M0 mu star lambda 3 lambda s, where mu runs over DC. So what I have done now, this computation, which I had to do with 1 million points, I have reduced it to 3 points and million minus 2 points. That's what I've done, right? Now, million minus 2 point, I keep doing this. I keep on subtracting. I subtract only 1 point here. So I could not have done with 2 points. I have to do 3 points. So I keep on going less and less. Now, so this M0, what 1 million point becomes sum over 3 points, but maybe so many copies. Now, there is a simple algebra which encodes all this information and spits out the result. Very easy algebra which can take care of this situation. But we have to worry about the 3 points. So we have to calculate the dimension of conformal block on P1 with 3 points. And that is encoded in what is called the fusion algebra associated with the Lie algebra G. And fusion algebra is basically, I mean, I will just say a one line explanation of that. That fusion algebra is you take the tensor product of representations of G, but you cut off at central charge C, the representations. I mean, this is not a very correct description, but this is an approximate description. So this information about the dimension of a conformal block on P1 with 3 point is encoded in the structure of the fusion algebra of the Lie algebra G at central charge C. So this is what is called the fusion ring of G at central charge C. Okay, so this is my very rough outline of the proof of Verlinde formula. I have not told you what the formula is, but this is how you prove. And this is, I mean, very simplified overview. As I said, the whole proof really runs into something like 200 pages. And there is recent book of I have a recent book in Cambridge University Press. I'm not trying to sell my book here, but there is a recent book, Verlinde formula and something. And that gives you a full proof. And there is a very parallel, beautiful story, actually a story which I like even more. This space is isomorphic canonically with the space of global sections of certain line bundle on the moduli space of vector bundles or moduli space of G bundles. So you take moduli space of G bundles or vector bundles on this fixed curve sigma, and this moduli space is a projective variety, and there are some line bundles which are called the determinant line bundles. Now you take the global sections of that. The dimension of that space is exactly this space of conformal block in some canonical way. And I have no time to explain that story, but it's, at least to my interest, it's even a more beautiful story. Okay, so I will not delve too much on the history, but there is this whole list of people who have contributed to this, and I'm not going to even repeat what it said here. Okay. So now comes actually, I don't know how many minutes I've left.
5.
Oh, you're only giving me 5 minutes? Okay.
Wait, no, 9. Sorry.
9 minutes.
Yes.
That's better. That's better. Okay. So this was really a prelude to this two-state theory. Now, this is now joint work with Jiuzu Hong. And what is the setting? So now we take still a reduced projective curve as we did earlier, a connected reduced projective curve. But now we involve an action of a finite group, which I'm going to call it gamma. So we have a finite group gamma, which is acting on this projective curve. And let's take the quotient of that projective curve by this group gamma, which I'm calling it sigma bar. And my curve was sigma. Okay, there is some technical assumption that we assume that gamma is acting faithfully on every component of sigma, irreducible component. Okay. Now, okay. Also, as before, we take a simple Lie algebra G, but this group gamma, the same group gamma, is acting by Lie algebra automorphisms. I'm not assuming any constraint on that. We are assuming that this group gamma acts on the Lie algebra G by Lie algebra automorphisms. So that's the second. Okay. So by S-pointed gamma curve, and this curve I'm going to call it a gamma curve. So curve with the action of gamma. So S-pointed gamma curve is by definition, as earlier, sigma, the points P1 through PS, PI are smooth points like before. They are distinct, but not only they are distinct, their gamma orbits are distinct. Now I'm going to assume that their gamma orbits are distinct. Okay. Now, to each pi, the point pi, earlier we associated a same affine Lie algebra, untwisted affine Lie algebra. But now, in this story, we have to involve the twisted affine Lie algebra. So let's take gamma pi to be isotropy of gamma at pi. So gamma is acting on this curve sigma, and pi is a point there. And I am not assuming anything that the action is of any particular type. So let's take the isotropy of gamma at the point pi. And let's just call it gamma sub pi. Okay. So let's take G hat, the affine Lie algebra as before. But now I'm going to take G hat, the corresponding twisted affine Lie algebra. G hat, the fixed point under gamma pi. So this is what is called the twisted affine Lie algebra. Gamma pi is some finite group. Gamma was a finite group. So gamma pi is some finite group. So we take that G hat pi. And just as now I am going to take to each pi, now I have a different Lie algebra attached to that. And that Lie algebra has its own parameterization of integrable highest weight modules, unlike the before. So now to each pi, I take DC at pi, which is the set of integrable highest weight module for this twisted affine Lie algebra. And just like before, we define H lambda to be tensor product of that, except that different Lie algebras are acting on that. Now, so this H lambda is a module for the direct sum of these Lie algebras. G hat P1, direct sum, so on, G hat PS. And the G hat PI part acts only on the ith factor. So that's the way it's going to act. And now we can define the twisted dual conformal block by taking H lambda and by quotienting it out by the Lie algebra G tensored with the affine coordinate ring of sigma minus gamma P, and we take the gamma invariants there. So I am taking the affine coordinate ring of G minus sigma P, so all the sigma orbits with values in the Lie algebra G, but I take the gamma invariants there. And it's going to act very similarly, except that at the point Pi, only that twisted Lie algebra is going to act. Okay, so again, the lemma is that this is space V sigma now with gamma P lambda is finite dimensional, and it does not depend upon the choice of local parameters Ti at the point Pi. Very similar. And the proof also is similar. Now, just as we had those theorems in the untwisted case, I am just going to say that propagation of vector is correctly stated. Factorization theorem is correctly stated. Existence of projectively flat connection on a smooth family is correct. And extension of connection to the Hurwicz stack with logarithmic singularity is correct. Oh, sorry. Thank you. Okay. So those results are correct. And they had the consequence similar that you want to calculate the dimension of twisted conformal block from a genus G curve, you can basically reduce to genus 0 curve. But genus 0 curve, creates some new issues because of this gamma action, which I will slop over. So we have proved a precise dimension formula similar to the Verlinde formula, but it has some new ingredients. And one of the new ingredients which comes in this to play, we took any gamma acting on the Lie algebra G, any finite gamma acting on the algebra G. First of all, we reduce the problem for any gamma acting on G by gamma acting just by the diagram automorphism of G. So it reduces the problem to a much smaller setting. And then there are many new ingredients, but I don't have time. So this dimension formula we prove. And also there is a different approach to the dimension formula proved by Deshpande and Mukhopadhyay. Right. I'm not right. Now, just as there was this geometric side that the dimension of conformal block was isomorphic with the dimension of some space of global sections on moduli space of G bundle, exactly there is a similar picture. We identify the twisted conformal block with the global sections on some moduli type, which was conjectured by Peppers and Rappaport. So we identify, so there is a geometric side. I will only say that I and Jiuzu Hong, we have 3 papers on the subject. They are all on arXiv. Actually, they are all more or less published. And altogether, it's a long project, something like, I think, altogether 140 pages, which covers the whole theory in detail with all the detailed proofs. And there is still something needs to be done still, but I can't explain that for lack of time. So whatever it's worth, this is the dimension formula in the classical setting.
Without the twisting.
Say it again?
Without the twisting.
Without the twisting, that's right. So this is the classical Verlinde formula. Now, yeah, the twisted, there is a similar twisted formula. It's a little bit more complex to explain for notation. But there is a similar dimension formula. So I think I am ready to stop.
Any questions?
Yes.
Thank you.
Okay, and in this case,
Yeah.
the fusion products.
What product?
In the classical case, you have a fusion product.
That's right. That's right.
In the twisted case,
Yes, there is. Yeah, it's a little bit more tricky, but yes, there is. Yeah.
is that similar to the Castello-State fusion products?
So say it again?
How is it related to Castello-State?
No, it's not. It's not understood. No.
Because that looks like a real.
See,
It's
okay.
algebra fusion.
Okay. Even the untwisted fusion product, I don't know if there is really a cardinalistic story there. Yeah, I don't know if there is a cardinalistic story.
Because Castello-State data for fix the level. Products.
That's right. Okay. So if that's the right, so the fusion product corresponds to, yeah, you have to be a little bit careful about that. So it's, yeah, exactly. So affine algebra at negative level. So so you take, yeah, that's right, exactly. So right. So there is no such interpretation, at least I know of, in this twisted setting.
So for your case, when you're modify gamma, you have this curve, algebraic curve modify this gamma, modify this gamma, finite subgroup. But then is it permuting the PIs also, where you have the
No. It's not permuting PI. In fact, I am assuming that the PI gamma objects are this one. So P1 through PS are smooth points in sigma. And the gamma orbits themselves are disjoint. Not only pi are disjoint, but the gamma orbits are disjoint. So it's far from being permitted. In fact, it's and the order of gamma and the number of points S, they have nothing in common.
Questions? Okay, so don't leave until someone's making an announcement about the types. What's that? Oh, you, perfect. Thanks.
So I should pass on this to you. Oh, you are here.